Chapter 5. In Chapter 4, we looked at ionic bonding model. But we also introduced, when we were naming compounds, we also introduced the covalent compounds at the end, type 3 compounds. That's where we're going to go today with the covalent bonding. These are compounds that are composed of nonmetals. You bond two nonmetals together, you always get a covalent compound. Okay, so we got a lot of ground to cover. So I hope I don't go too fast, but it's all recorded, so you can go back and look at it again. Okay, the key differences between ionic and covalent bonding. The obvious one is that ionic bonds are between metals and nonmetals because there's a complete transfer of electrons. Metals tend to give up their electrons. That's how they attain the noble gas configuration of their electronic structure. And nonmetals tend to accept electrons. That's how they tend toward noble gas configurations. Whereas ionic bondings involve electron transfer, covalent bonds are sharing. So each of the atoms thinks it has the noble gas configuration, but we don't add or subtract any electrons. They just, by sharing the electrons, I guess you could think of it as inventory. When, if I'm, look at it this way. If I've got oxygen and hydrogen in a water molecule like that, okay, so this one is donating 1 electron. This one's donating 1 electron here. But this one needs 2 electrons to look like neon, right? We talked about that last week. So if oxygen combines in an ionic bond, it actually gets those electrons and it keeps them. But in a covalent bond, it has to share. So when the inventory time comes around, it says, oh, look, I've got these 2 other electrons. I must be neon. But when hydrogen's inventory time comes along, it says, wait a minute, I need that electron so I can look like helium. So that's kind of the way to think about the sharing. Whenever they think they need to look like the noble gas, they always have access to not just their region, but the bond incorporates those electrons into the structure and gives it that noble gas configuration. All right. Ionic compounds don't contain discrete molecules. In other words, they're more of a lattice of positives and negatives, cations and anions together in a lattice. And I think the example I used was sodium chloride, where you have sodium ions surrounded by chloride ions. And then if you look at a chloride ion, oh, it's surrounded by sodium ions. And they're in a matrix, a crystal lattice, we call it. But for covalently bound compounds, they are discrete molecules. In other words, that water molecule is separate from all other water molecules. And the only types of interactions that it experiences with other molecules come under the category of painting myself into a corner. Intermolecular interactions. It's sort of like bonding, but it's not. It's an attraction, but it's not a bond. And hopefully we'll get to talk about that a little bit as we proceed. So when we say a molecular compound, we're implying covalent bonding. Ionic bonds, we're implying crystal lattice with positives and negatives throughout. So when we write the compound for an ionic, when we write the formula for an ionic compound, we're actually saying this is the simplest whole number ratio of cations to anions. We're not saying that's a discrete molecule, but when we write a covalent compound like H2O, we're saying that is a discrete molecule. Now, how do you tell the difference? The ionic bonds are going to be metal nonmetal, whereas the molecular forms are going to be both nonmetals. That's the giveaway. All ionic compounds are solid at room temperature, and they have very high melting points. It takes a lot of energy to break those electrostatic attractions between the positives and negatives. Whereas covalent compounds can be solids, liquids, or gases. And the principal reason for that is those intermolecular forces that hold them together. That's what determines their state. So if the intermolecular forces are strong, they might be a solid. If they're a little weaker, it could be a liquid. If they're weaker still, it could be a gas. Okay, like hydrogen sulfide is a good example of a covalently bound compound that's a gas. I drive through Greenbrier County and stop and get a drink of water, and you'll taste some of it. It'll come right out of the water in your face. Well, not every place, but several places, like green sulfur springs, white sulfur springs. Right? That's how they got their name, because it's stinky water. When an ionic solid is soluble in water, and that chart that I showed you with the gray boxes on it tells you whether the ionic solid is soluble in water or not soluble in water. But when it's soluble in water, it breaks apart into individual ions. When it does that, now water can conduct electricity. Pure water is an insulator because it's a molecular compound. It doesn't form ions. And in order to complete a circuit, you need something to transfer the charge. Remember, in electricity, electrical, they don't call them circuits for nothing, that's circular, right? You don't get current flow in a circuit if it's broken. So if we put two electrodes into water, then there's no circuit, right? A light bulb in that circuit won't light. But if you put some sodium chloride in there, an ionic solid that dissolves, breaks up into individual ions, now the charge can be transferred between electrodes by those mobile ions. You can also do that with melted sodium chloride. You can heat it up hot enough to where the ions are now separated in the liquid form, and it will conduct electricity. That's characteristic of ionic solids that form aqueous solutions, whereas covalent compounds usually produce non-conducting aqueous solutions. We say usually, because there are cases where they will shed parts of themselves and make ions. For instance, acids. If you put HCl, gas, hydrogen chloride, dissolve it in water, now it's hydrochloric acid. It completely dissociates into those ions. It will conduct electricity. So it might be a covalent compound, but that's one example of a covalent compound that dissolved in water will conduct electricity. So whereas ionic solids always conduct electricity if they dissolve in aqueous solution, only some covalent compounds will do that. Okay. I mentioned covalent bond is the sharing of electrons. That's true. Whenever we write one line like this between two atoms, that represents two electrons. If we have another bond between those two atoms, which can occur, a double bond, that's two more electrons. So for every bond, you're talking about two electrons. So a double bond would be 4 electrons in the bonds, and occasionally you can get triple bonds. Now you got 6 electrons between, and those are particularly strong. As you increase from single to double to triple bond, you get a stronger bond. It's not linear. In other words, triple bond is not 3 times as strong as a single bond, but it does increase in strength. Okay. Example, hydrogen shares 1 electron from each side, makes a bond. The concept here is that they're the orbitals that were once occupied only by this 1 electron, the orbitals, which is represented by this shaded area, overlap. And now the electrons are free to occupy this space. Come in, sign in, and grab any one of those that you don't already have. So the overlap of orbitals is one explanation for this sharing of electrons. So we drew Lewis dot structures for some compounds, the ionic compounds. You can do the same thing for covalent compounds, Lewis dot structures. Let's see, there should be some more complicated ones that would illustrate better. I'm going to skip those things. Okay, here we go. Lewis dot structures for, let's see, difluorine. Fluorine is a diatomic element, so normally it prefers to have 2 fluorines together. So if we know that fluorine is going to be diatomic, then you draw your Lewis dot structure and you find out how many valence electrons does it have. Well, it's a halogen, so it has 7. Right? 1, 2, 3, 4, 5, 6, 7. And the Lewis dot structure gives you a bond here. So now this one thinks it has 8, and that one thinks it has 8, and we got a bond. All of these others are called non-bonding electrons. These guys right here, they're not part of the bonds. But we can also call them lone pairs. In fact, when I refer to them in the future, I'll probably call them lone pairs. Lone pairs are not involved in bonding. Okay. I mentioned single, double, and triple bonds. This just illustrates that. Hydrogen only has 1 electron. So a single bond is its only option. It forms a duet, right? You got 2 electrons assigned here, 2 electrons there. It thinks it's helium. Double bonds, carbon dioxide. So you can form, oxygen tends to form 2 bonds. Why? Because it has 1, 2, 3, 4, 5, 6. Yeah. 6. Well, let's do it this way. Normally it would be like this, like that, like that, like that. So now it has 6 electrons in its valence shell. And when it comes in contact with a carbon, carbon only has 4. So it forms a bond here, right? But it needs to form another one. Now oxygen has 8, but carbon still doesn't have its octet. So it goes to the oxygen on the other side and forms a bond here and here. So double bond on that side, double bond on that side. And that gives you the octet for both of them. So the formation of single, double, triple bonds is dependent upon whether we can create an octet by doing that. If we've got a molecule where there's just nitrogen, Nitrogen starts off with 5 electrons, 5 valence electrons, which means it has 2 in a pair, and then it has 3 unpaired. So one bond between that pair, one bond between that, one between that. So it has a triple bond between nitrogens. That's why nitrogen is so very stable. It has that strong bond. And that's the way it is in the atmosphere. Plants can't use it, not like that. And they don't have the enzyme systems to convert this to something they can use, like nitrates or ammonia. So that's why the ones that can convert nitrogen gas to something that's called fixed nitrogen, that they can use to build proteins primarily and nucleic acids, they have a symbiotic relationship with microorganisms, usually in their roots. So if you know anybody that grows soybeans, clover should do this too. They're legumes. In other words, they have the ability to fix nitrogen. If you pull up a soybean plant and look at the roots, you'll have little nodules on it. That's where the rhizobial bacteria live. If you cut into them and they're pink, that means they're active. They have something called leg hemoglobin that does similar things to the hemoglobin in our system, transfers oxygen. But that means they're active. And they're taking this nitrogen from the atmosphere and turning it into ammonia so the plant can use it. And then the plant supplies them with energy. So it's a true symbiosis. Okay, how many electrons are in a double covalent bond? 2 times 2 is 4, right? Okay. Most nonmetals have a tendency to form a certain number of bonds. I mentioned oxygen. It tends to form 2 bonds. That's all it needs to complete its octet. So that could be a double bond or it could be 2 single bonds. For water, it's 2 single bonds with hydrogen. For carbon dioxide, it's a double bond with carbon on one side and another double bond with carbon on the other side. And it all depends upon how many electrons do they need to complete the octet. So oxygen tends to form 2 bonds in some form. Nitrogen tends to form 3 bonds. So it could form 3 bonds here, like if we put a hydrogen, 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 that's ammonia. Or if we put, let's see, hydrogen and oxygen, that would be, well, we'd have to dissolve it in water, but that would be nitrous acid. Or if we formed a triple bond with another hydrogen, of course, that'd be the one we've already looked at. Carbon tends to form 4 bonds. And that leads to enormous complexity because you can have strings of carbon together or branched carbons. Right? You can have a carbon, 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 or you can have 4 hydrogens and make methane. Or you can have 3 hydrogens and chlorine and make chloromethane. Or you can have, well, you can put 2 oxygens here, right, make carbon dioxide. So that's why organic chemistry is so complex, because carbon, which is the basis of organic chemistry, can form 4 bonds of so many different types.
Can you not have a tetrabond, or is triple bond limit?
It's not normal. I don't doubt that researchers might be able to force it. They could force it, and they probably have. Put 2 carbons together and force them to do that. It's difficult to do once you understand how those bonds are formed. I don't want to give you too much detail, but the bond that forms on axis with the 2 atoms is called a sigma bond. And then you have orbitals that go like this, they can overlap and make a double bond on this plane. And then you have the others that make a double bond on that plane. So that sort of limits you to 1, 2, 3 bonds. But a fourth one, I don't doubt that they've tried. Interesting question. I don't know the answer. How many covalent bonds can oxygen form? 2. Oops, skipped. Okay, there's a special kind of covalent bond. Up to this point, we've said we're sharing electrons. So one electron is donated from one atom and another electron donated from the other makes a bond. There's a type of covalent, coordinate covalent bond in which both electrons are donated by one atom. Now, the thing about that is, after the bond forms, after the molecule is formed, it looks like any other bond. You don't know that it has formed from 2 electrons from one atom rather than sharing the 2 to begin with. So the only way to tell that it's a coordinate covalent bond is to know how the reaction occurred. But it does enable an atom that has 2 vacancies in its valence electron shell to share a pair of non-bonding electrons from another atom and complete its shell with a bond. Let's see, are they going to give us an example? Yeah, here we go. So if we have this possibility, this molecule is already complete. See, we've got 2, 4, 6, 8, 2, 4, 6, 8, and 2 for hydrogen. But if oxygen comes in, oxygen needs 2. So if it takes 2 from this chlorine and forms a bond, everybody's still got their octet. So why would it want to do that? There has to be a driving force. Reactions don't occur by accident. There has to be some reason. There has to be a force. They have to be lower energy afterwards. Well, not always, but they tend to be lower energy after the reaction. They're always a more stable situation. Let's put it that way. They're more stable after the reaction occurs. So if this confers some stability, then yeah, that reaction is going to occur. And maybe you have special conditions that are involved. You have to force it. Okay, so that's an unusual type of covalent bond. And the only way we know that this, if we just had that, there's no way to tell it was coordinate covalent. We could propose it as a coordinate covalent bond, but we'd have to prove it by doing this reaction and forming that compound. Then we know it was coordinate. Okay. This just talks about coordinate covalence some more. I want to skip that. And I've already mentioned this. There's other examples. This particular, let's see, nitrous oxide, which is laughing gas, forms one of those bonds, right? If we look at just the dinitrogen, they're complete. But this oxygen comes in and finds it's got this extra pair of unused electrons, forms a bond. Okay, so that's a coordinate covalent bond, nitrous oxide. Carbon monoxide. In this case, that's kind of odd. Now for, let's see, 2, 4, 6, 8, that's okay for carbon. 2, 4, 6, oh, that's okay for oxygen too. But normally what we would expect is for oxygen to form only 2 bonds. But in this case, it forms 3. This is kind of unusual. But if you count up the electrons around that oxygen, and each bond has 2, 2, 4, 6, 8, okay, oxygen's got its octet. But carbon monoxide is still very reactive. That's why you don't want to breathe it. It attaches itself to iron more strongly than oxygen does in your hemoglobin. and it won't let go. So you actually suffocate on a molecular level if you're exposed to carbon monoxide. Okay. Lewis structures. Okay. So if we're going to do a Lewis structure for a covalent compound, all you have to do is you have to be given the formula, the correct formula for the compound. So this sulfur dioxide is a correct formula, and you add up the valence electrons for each of the atoms. So if we have a sulfur, which is in the oxygen group, so sulfur has 6 valence electrons. Oxygen has 6 times 2 is 12, or 3 times 6 is 18. So we have a total of 18 valence electrons. Then you position them. You have to decide which one is the central atom. In this case, sulfur is the central atom because of the way it's written. It wouldn't make any sense to put oxygen in the middle. It tends to be, if you can balance the structure, do it. So rather than write oxygen here and a sulfur here and an oxygen there, that's unbalanced. So a sulfur in the middle with oxygens on either side is balanced. But we have 18 electrons to deal with. How many have we used so far? 2, 4. We used 4 electrons. So that means we have 14 left. And you start from the outside and place them working in. So we have 14. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, minus 12 is 2. So we've filled up the octet on oxygens from the outside working in. So we get 2, 4, 6, 8. That's all they can hold. So now we've got these other 2 electrons. Where do they go? Well, they keep moving in. They go here. Okay. The problem with that is sulfur doesn't have an octet yet. It's only got 2, 4, 6. So now, how can we make an octet for sulfur without depriving oxygen of its octet? You take 2 of these electrons and make a double bond. Right? So now we got a double bond here. Right? Those are used up. So now we got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. Okay. The problem with this is, and that's a problem with the Lewis dot structure method of drawing these structures, is that we could just as easily have come from the other side. Right? So we have 2 equivalent Lewis dot structures. Right? The other one would look like this. Like that. So what do? Well, the model that we're using doesn't allow for partial bonds. They've got to be whole bonds or nothing. So we have to, it's like any theory that has a failing. You're right, you have 3 options. Remember that? What do you do if your theory fails? Right? Toss it and start over. That's one possibility. Or modify it. Right? Say, all right, we're only going to use it. Well, we change something about it to make it work. Or you restrict its use. You say we can only use it under certain circumstances. In this case, we're going to modify it with a concept called resonance. So we're going to say, okay, both of these are equivalent, they're valid, so we're going to resonate between the 2. Say, that's our Lewis structure. It resonates between those 2 structures. Now, how do we know that they're basically equivalent? Well, when we measure the bond strength and the length of these bonds, they're exactly equal on both sides. This one is not stronger than that, or that one's not stronger than that one. It's kind of in between. So the real structure is in here somewhere, caught in mid-resonate. It's in there. Okay, so that's one of the failings of the model that we're proposing. All right, so I gave you the contents of the next few slides, probably. You put one bond between them. I used a line instead of dots for electrons. And that's where you start. And then you start placing your extra electrons until you get down to this place. And we got 2 more electrons left over. And they have to go here. But, like I said before, we have to make a double bond in order to complete sulfur's octet. Now, if you can complete the octet, do it. But if you can't complete the octet, there are cases where we have incomplete octets, or we have excess of octet. We have more than 8. Those are possibilities. And we just have to deal with it, right? Because nature does what it does, and we've got to explain it. So we know that this compound exists. Boron trihydride. A boron has what? 3 valence electrons? And 1 from each of these is 3. So we have 6 valence electrons, right? Okay, so we put boron in the middle, and hydrogen's out here. 2, 4, 6. Used them all up. Boron doesn't have an octet. And there's nothing we can do about it because we don't have any electrons to put in there. So that's one example that's has a deficiency. But it is a stable compound. So we just have to live with it. Okay, Lewis dot structures for each one of these. That one's simple. You've only got 2 electrons to deal with, 1 from each hydrogen. Fluorine only has 1 available for bonding, and that gives it an octet. Remember, hydrogen is the duet rule because it only has the, let's see, we've done electronic structures, so you know it only has a 1s orbital, which makes available for 2 electrons. That's it, we're done. But fluorine has s and p orbitals available, so it could have 8. And then HF makes, this one has a duet and that one has an octet now. Ammonia will look like this. It'll have 1 lone pair. Okay, 2, 4, 6, 8. Now, do we have the right number of electrons? Valence electrons. 5 plus 3 is 8, right? Okay, 2, 4, 6, 8. Okay, we didn't cheat. Carbon dioxide, we looked at that one already. Carbon tetrachloride. Chlorine's got to have 8. Carbon's got to have 8. Carbon starts with 4, so it has 1 from each one of the chlorines to complete the bond. And now each of them has 8 electrons. What are the total number of dots in the Lewis structure for SO2? Did that one already, didn't we? It's 18. We counted them up. What do we do with polyatomic ions? Polyatomic ions are special. The whole group is bound with covalent bonds. That's why it holds together in a single structure with that charge distributed over the whole structure. It's covalently bound ion. And then it can interact with metals. Most of them. Ammonium, of course, takes the role of a metal because it's positive, but the rest of them are negative. There's only one other positive I know, and it typically doesn't form bonds anyway. It's the hydronium ion. We'll talk about that when we get to acids. We already talked about it. Oh, that's later. Okay. We'll say the hydronium till exam 4 discussions. Okay. So when you draw the Lewis dot structure for a compound that has a polyatomic ion in it, it's best to do the polyatomic ion as a separate unit and then bond it with the ions, the cations in this case. So this would be our Lewis dot structure. And when you do SO4 with a 2- charge, adding up these, sulfur and oxygen in the same group, they have 6. 5 times 6 is 30. Don't forget those 2 electrons. So you have 32 electrons that have to be positioned. And then when you draw the structure, be sure and put brackets around it with the charge. Because if it doesn't have that charge, then you got too many electrons. Okay? And this shows you how not to write it. Because potassium is not covalently bonded to these guys. It's electrostatically attracted because of the charge difference. Okay, so SO4 2-, we counted that one up, it's 32. I'll do that. Yeah, 32. Okay, now what good is the Lewis dot structure for our molecules? We can use the Lewis dot structure to say something about the geometry of the molecule. Now, why would we want to say anything about the 3-dimensional arrangement of the atoms? Because that way we can imply whether or not that molecule is polar or nonpolar. In other words, does it have an uneven distribution of electrons? So that will determine how it interacts with other molecules, even other of its neighbors, same molecule, or any other thing you put together with it. That's why when you put certain types of compounds in water, some of them dissolve and some of them don't. It's because of this interaction that we can infer from the structure of the molecule. Okay, so what we want to do is determine polarity. And we use this model, the valence shell electron pair repulsion model, the SEPR. All it says is that we're talking about only the valence electrons. We've already done that. We know what they are. And they occupy their positions in pairs, either lone pairs or in bonds. And we try to minimize repulsive forces. So how do you minimize repulsive forces between like charges? You get them as far away from each other as you can. And if they're restricted to a molecule, you position them around the molecule, I would say around a central atom, so that they have minimum repulsive forces. You wouldn't want to draw the water molecule like this. Those electrons are too close. They may be in bonds, but they still are both negative. So they're going to repel. Right? So we position them as far apart as possible, except what else do we have here? Oxygen forms 2 bonds, but it also has some lone pairs, right? 2, 4, 6, 8. So in order to position all the electrons in a way that minimizes the repulsive forces, we need a regular geometric structure that allows us to position these 4 electron groups, that one, that one, that one, that one, as far apart as possible. And the structure is a tetrahedron. So if we put oxygen in the middle, then we can put hydrogen here, hydrogen there, lone pair back here, and a lone pair out there. That puts them as far apart from each other as possible. So whenever you have 4 groups around a central atom, it's always a tetrahedron. Now, you can't see the electrons here. we know they're there, but you can't see them. So what is the molecular structure? Well, all you have to do is just cover these up, right? And let's move these into a better position. It'd be more like this, that. If you cover up those lone pairs, now what do you have? You have a bent molecule. So that's your structure. Your molecular structure is a bent molecule, while the electronic structure is a tetrahedron. Okay? So the moral of that story is you got to go through this one to get to that one. And that's VSEPR in a nutshell. Okay. The VSEPR says valence shell electron pair repulsion. I disagree. The way the theory is used is based upon electron group repulsion. So if we have something like this, excuse me, give myself some more room here. If we have this one, carbon dioxide, okay. This has got 2468, 2468, 2468. We focus on the central atom. What's the geometry around that central atom? It's only got two groups, not just two pairs. So valence shell electron pair repulsion, and maybe you could stretch your imagination to say, okay, this one repels that one and that one. Okay, but if for a practical matter, there are two groups here. And whenever you have two groups, they form a linear structure. That's as far apart as we can get those guys, is a linear structure. Now, of course, if we focus on this one, the electronic structure here is 1, 2, 3. So that's called trigonal planar. It's an isosceles triangle in a plane. Whereas this is linear. Now I'm going to show you what the significance of that is in a minute. As far as polarity goes, you need to know two things to determine the polarity of a molecule. The polarity of the bonds and the geometry. Because this polarity says the electrons are drawn toward oxygen because it has a stronger pull. We haven't talked about electronegativity yet, have we? I don't think we have. And this one pulls that way, right? But they're equal, right? This oxygen and that carbon, that makes that polar bonds, those are equal but opposite directions. They cancel each other out. So that means this molecule is nonpolar. It doesn't have a polar nature. Overall, you still have the polar bonds. So this nonpolar molecule isn't the same as some other polar molecule, say, is like this. That's linear also. But it's nonpolar. It's more nonpolar than this one is. Because that bond can't be polar. Because those are identical atoms. See what I'm getting at? There's polar, and then there's polar, and there's nonpolar, and then there's nonpolar. Or what's that famous quote? A rose is a rose is a rose. Maybe it is, maybe it isn't. All right. So I'm spending too much time on that. Okay, so when you use this model, you have to have the Lewis dot structure drawn. You got to draw the Lewis dot structure, find out where are your atoms positioned in that molecule. Then you find out how many groups of electrons you have. Count the lone pairs also. Lone pairs and bonding electrons. Count if you have a single bond, double bond, triple bond, that counts as a single group. Okay, and then the lone pairs are independent players. count up those numbers. And then we use the numbers of those around some central atom. For small atoms, there's only going to be one central for small molecules. For big molecules, you can have several different centers that have different molecular shapes. And then you go to what is the geometric shape that gives you the least repulsion among those groups. All right, here's linear. If you have three, either bonding or a lone pair and some bonds, that's trigonal planar, right? Equilateral triangle. That's the only possibility. If you have four, like these examples, methane, ammonia, water, their electronic geometry is tetrahedral. Then for this one, the molecular geometry is also tetrahedral because there's an atom at each one of those apexes of the tetrahedron. For this one, you got that one at an apex. So that means this molecular geometry is a trigonal pyramid. Right? It's got a trigonal base with nitrogen at the apex of the pyramid. And this one, since they got two pairs there, they call it angular. I like bent. Because angular could be anything. I think bent works better. Let's see. Oh, examples of more than one central atom. So what's the geometry around this one? 1, 2, it's linear. 1, 2, it's linear. How about this one? 1, 2, 3, 4 around that one. Right? That's tetrahedral electronic. And then it's bent molecular. And this one's also bent molecular. That's hydrogen peroxide. This one is going to be linear. This one is going to be trigonal planar. But if we cover up that electron, that means it's bent as a molecular structure at that place. Okay? All right, that just shows you what we talked about a second ago. All right, so I think I got this out of my book. No, let's get that out of your book. Yeah, you should find this in your textbook. So this gives you the electronic geometry for these numbers of groups. Right? If you have 2 around the central atom is linear, 3 is trigonal planar, 4 is tetrahedral. If you have 5, then you're going to have 3 around the central and then 2 at either apex. So it's like 2 trigonal pyramids base to base, right? A trigonal bipyramid. And then I stop at this one. If you have 6 groups, it's like 2 pyramids with a square base. It's octahedral. Okay, so this is the structure for the electronic structure for that many groups. And if each one of these positions is occupied by an atom, it's also the molecular structure. It's only when we have lone pairs involved in this arrangement where you have a deviation from the electronic structure to the molecular structure. I think it's on the next slide. Yeah. And we showed examples of these already, right? If you've got 1 lone pair, here's trigonal pyramid. If you've got 2 lone pairs, it's bent. If we start with a trigonal bipyramid, right, we're going 1 step beyond tetrahedron. Then if one of them is a lone pair, the preferred version is a seesaw, right? Just take this thing and put it on the side. There's your base of your seesaw, and here's the teeter-totter. So that's for 1. If you have 2, the possibility is T-shaped, right? So what happens with these lone pairs is the bonding itself confines the electrons in the bond to that region between the atoms. But if they're lone pairs, there's nothing constraining them on the other side, so they tend to balloon out. And when they do that, that puts pressure on the other bonds to bend. Okay? So what we try to do is minimize that effect. The bond angle in a tetrahedron here, that bond angle is 109.5 degrees. But if we have a lone pair up here, this bond angle shrinks to maybe 108 degrees because there's pressure from this ballooning here that pushes those down. And for something like water, you've got two lone pairs pushing on that bond. So that bond angle, I don't know, it may be 106. I'm just guessing, but it does decrease. Okay. And if we have a trigonal bipyramid with three lone pairs, the best option there is to put those lone pairs in the plane of the triangle and put your atoms on the end, and that makes a linear molecule. Okay, I'm gonna skip those and these. Electronegativity. Okay, electronegativity is an expression of the attraction of an atom to an extra electron. So if you take the neutral atom and you say, how strong will it attract another electron? We've already sort of implied from our discussion of the difference between metals and nonmetals. Metals tend to have a low electronegativity because they'll give up an electron pretty easy from the neutral atom. But neutral atoms of nonmetals tend to attract electrons to themselves. So they have a higher electronegativity. And the trend is the electronegativity increases from lower left to upper right in the periodic table. So the least electronegative atom is down here around cesium. And the most electronegative is fluorine. We don't even consider the noble gases because they're happy. They don't want to give up electrons. They don't want to take any more electrons. So we just leave them alone. And there's a numbering system for that electronegativity. The highest you can get is 4.0. And this is in the Pauling system. It's 4.0. And I think cesium is down around 0.7. Okay. Now it's close. Well, that doesn't go down to cesium. I think cesium is actually 0.7. And there's a way to calculate these, but we're not going to go into that. It's just, this is it. So from lower left to upper right, we increase electronegativity. That also means that as you increase in a family, in a group, you get higher electronegative. And if you go from left to right in a period, you get more electronegative. So what's the practical application of that? Well, if you have a bond between two atoms, and you don't know whether it's ionic or covalent, you just say, what's the difference between their electronegativities? Right? If they're very close together, right, it's going to be a covalent bond. Plus, is it going to be a polar covalent bond or a non-polar covalent bond? So we have sort of a rule of thumb that goes along with that. So you say the difference in these two, say between boron and fluorine, that's a difference of 2.0, right? So we go to, let's see. Well, I thought I was going to get to it here. Here we go. 2.0. If the difference is 2.0, then it's just the beginning of ionic. We're getting bigger as you go down. So the difference is 2.0. It's sort of a mishmash between ionic and covalent. Anything bigger than 2.0 is ionic. If we get less than 0.4 difference, then we're saying it's non-polar covalent. If we get less than 1.5 to 0.4 to 1.5, we say that's polar covalent. And if it's between 1.5 and 2, we say it could be ionic or it could be polar covalent. It depends on whether you've got two nonmetals or a metal and a nonmetal. If it's a metal and a nonmetal, we're going to call it ionic if it's bigger than 1.5. But if it's two nonmetals, we're going to say, we're still going to call it polar covalent. So it's kind of a gray area. All right, let me go back. All right. So which one of these would have a stronger attraction for electrons? Lithium or fluorine? Lithium is to the far left. It has a lower electronegativity than fluorine. Fluorine has a stronger attraction. Okay. How about in a bond between fluorine and iodine, which has more attraction? Fluorine, because it's above iodine. And you can get bonds between halogens, two different halogens. Right, so fluorine is still more electronegative and tends to attract electrons to itself more strongly. The question then is it polar or nonpolar? Okay, which one has the highest electronegativity? Well, helium doesn't count. Oxygen is up and to the right of everything except for hydrogen. And hydrogen sort of sits off by itself. So the concept of bond polarity depends upon the difference in electronegativities between the two atoms that are sharing that bond. The greater the electronegativity, the more tendency toward polarity. And then we have to use those numbers to say whether we think it's polar or nonpolar. Right? That would definitely be nonpolar, right? Because they're both equal atoms. Right? That's a no-brainer there. How about hydrogen and chlorine? Well, we have to look at the difference in electronegativities, and typically it's considered polar covalent. And this is the way we represent it. This is going to be the positive side, so we use this little Greek delta. The capital delta is like this one. Seeing that in math class, delta is the difference. We use a little delta with a sign on it, and that says it's not a complete charge. It's only a slight charge, slight positive, slight negative by comparison. Because we can't give it a complete charge because this is a covalent bond. You can't transfer electrons over here and leave them away from that one. Now you have an ionic bond, and you would put a complete charge on it. So we have to use this symbol. And we also use this one. This arrow says that's the direction the electrons prefer. They spend more time over here. And this says that's the positive side. So this is a vector arrow. It gives you both direction and magnitude. Now, we usually draw them one length, or sometimes we draw them a little bigger to emphasize. So it's not quantitative, but it does show you direction. And we already looked at that one. Okay. So arrange the following bonds in the descending order of polarity. The nice thing about this first one is they're all bound to fluorine. So all you have to do is say, look at how far are these away from fluorine. Well, let's see, nitrogen here, 2 steps over, oxygen's closer, and then carbon is even further away. So the more polar is carbon and fluorine. It's further away to the left. And then comes oxygen, and then comes nitrogen in descending order. Okay. And these we have to look at the difference here between these two atoms. Carbon and fluorine are pretty far apart. Nitrogen and oxygen are very close together, so they're not going to have much of a polar bond, if any. And silicon and fluorine are even further away than carbon, because silicon is in the carbon group, but it's down below it. So that, remember, lower left to upper right. So this one would be the most polar, then this one, and then that one. Now these, that's nonpolar. Right? 2 equal atoms. Boron and chlorine, they're pretty far apart. Sulfur and chlorine, they're closer together. So this would be the most polar, this would be next, and then that one would be the least. Okay, that's how we rationalize that selection. Which one would be the least polar, yet still be considered polar covalent? Okay, if it's going to be covalent, we got to get rid of the ionics, right? Right, so that's a metal, nonmetal. Don't even consider it. Got any more metal, nonmetals? No, okay. Polar covalent. Those are equal, they don't count either. That's nonpolar. So we have the potential for polar here, here, and here. So which one would still be the least polar? The ones where they're closest together in the periodic chart. Carbon and oxygen are 2 away from each other. Silicon and oxygen are 3 away from each other. Nitrogen and oxygen are next door. That would be the least. There we go. Bring this up. The most polar, without being ionic, would be the silicon and oxygen. They're furthest away from each other. Okay. Let's see, I'm going to skip that. All right, so now that we are able to determine the geometry of molecules, then we can combine the polarity of the bonds with the geometry to determine if the molecule is considered overall polar or nonpolar. I showed you this one earlier. That's nonpolar because this bond may be polar, carbon and oxygen, but they're opposite and equal, so they cancel each other out. So that would be nonpolar. This one, on the other hand, water. These bonds are nonpolar, but they're not, they don't cancel each other out. In fact, they reinforce one another. So for the entire molecule, the vector would be this way. This one would also be polar because this is polar that way and this one's polar that way. So they add up to a polarity in this direction. Okay. So there again, we need to know the polarity of the bonds and the geometry to determine if a molecule is polar or nonpolar. Okay. Let's see. I'm going to blast through these polar compounds. Let's see. Oh, I didn't even give answers for this one. Beryllium is another example where you have a deficiency. Beryllium is not going to have an octet. Beryllium only has 2 electrons. It forms a bond with one chlorine on one side and the other chlorine on the other side. It's a linear molecule and it's nonpolar. It has a deficiency of an octet. So water is the only polar one out of this one. This one is a tetrahedron. And even though the bonds may be slightly polar, they balance each other out because it's a regular structure and they're all combined. You can say the same thing about carbon tetrafluoride. Okay. We've already named binary molecular compounds. Those are the type 3s. Right? So we don't have to spend a lot of time with these. Two nonmetallics together form a binary molecular compound, and we know how to name them. You just say, how many atoms are there? Like carbon dioxide or dihydrogen monoxide, water, or diphosphorus pentoxide. Okay, so we know how to do that already. I incorporated that into chapter 4 discussion because it just tended to flow better. Okay, and you've got these prefixes that you have to know in order to name it correctly. I just need 1 through 10, that's all that I'm going to have you memorize. Greek prefixes for the numbers. Common names. Hydrogen peroxide. Okay, we're saying hydrogen peroxide when we typically, systematically, we would say dihydrogen dioxide. But we know that it's actually this. And that is a peroxide. So we say hydrogen peroxide. These are common names. Ammonia, hydrazine, N2H4, methane, ethane. Now we're getting to naming organic compounds here, these two. Nitrous oxide. Actually, dinitrogen monoxide would be proper here also. But nitrous oxide is typically used because it's laughing gas. And once you breathe it, you kind of lose all perspective. And nitric oxide is the one that they're hawking from super beets. You take those super beet pills or you mix it in your drink. It's supposed to boost your nitric oxide, which tends to dilate your vessels and give better blood flow to the rest of your body. Okay. That one, phosphorus pentoxide, we've left off the di, but the rest of them are named properly. Penta is 5. And we got these concepts here. I'm going to let those go.